Hello, my name is Brandon. I'm a research associate with the Arctic Hydrology Research Group here at Laureate, and today I'm going to talk a bit about an ongoing project mapping spatial heterogeneity of snow for polygonal terrain. This project builds on a recent one we initiated this summer at the Trail Valley Creek Research Station, looking at ongoing changes to catastrophic thermal karst lake drainage. Many areas of the Arctic are dominated by an immense number of lakes, covering up to sometimes 50% of the land surface area. And these lakes provide important habitat for fish, waterfowl, mammals, as well as influence cultural well-being through travel and access to the land, hunting, and fishing. And most of these lakes formed from melting of massive ground ice over the past millennia. So these thermokarst lakes are susceptible to a process called catastrophic thermokarst lake drainage, whereby melting of massive ground ice near the outlets or perimeter can result in a rapid emptying of the lake in sometimes a matter of hours or a few days. And strangely enough, there's been an increase in the rate at which these lakes are draining in recent decades, which sort of begs the question, what's driving this recent change? And there are many suggestions, but one of those being that degrading ice-wedge polygon features near the lake outlets are one of the main causes of this rapid draining. Polygonal terrain are widespread and characteristic of permafrost regions and are found all across the north. An example of this here in the background of this slide is an ice-wedge polygon field. And these ice-wedge polygons develop in permafrost regions as winter thermal contraction results in cracking of the frozen ground. In the spring and summer, when everything melts out, water accumulates in these cracks, which eventually refreezes, forming an ice wedge. And this process repeats year after year until a large ice wedge is formed. Now, under a rapidly warming Arctic climate, winter temperatures are no longer reaching the minimum lows that they used to, which could be resulting in a decrease in winter thermal cracking of the landscape. Furthermore, rapidly warming air temperatures across the circumpolar Arctic are thawing permafrost, and ice wedge polygon fields in general are degrading. And when you combine this with increasing active layer thaw, warming ground temperatures, and changing snow patterns, these permafrost features are at risk and are expected to lead to many changes in the surface hydrology of these freshwater lakes and streams. Now, thawing of the ground ice at the lake perimeter can also alter surface water runoff, which can then affect discharge patterns. And so our goal here is to model these events using modern hydrological models, but in order to do so, we need to have field data and observations at scales comparable to what we can run our models so that we can test and validate them. And this here is an example of a catastrophically drained thermokarst lake in the Trail Valley area. And this lake here drained many decades ago in a very rapid drainage event that would have taken place over maybe a few days. And so we see here that within the drained lake basin there is a new lake beginning to form. And so our goal is to try to maybe model these events looking at drivers of drainage and how the hydrological system in general is going to respond. And so to do this, we've instrumented a few ice wedge polygon fields to try to better understand the thermal conditions and the below surface temperatures. So the focus of this talk here is, of course, on using drones to map snow. And you might wonder how this fits into draining thermokarst lakes and ice wedge polygon fields. Well, snow is the main driver of the hydrological system across most of North America. So if we want to understand anything with relation to fresh water, we need to understand how much snow is falling in these areas. And so our focus here was to collect high resolution observations of snow for validating ongoing ground surface temperature modeling. So we had three main objectives here. We wanted to map snow distribution at a very fine resolution. We need to estimate some snow water equivalent, how much water is being stored across the landscape. And of course, we want to use this data to incorporate into the models to try to get a better understanding of what's going on. So to start, we needed to produce snow depth maps at resolutions comparable to our models. And this is something that we've been doing for many years now. We used a fixed wing EB to map late winter snow depth across the key areas of the Trail Valley Creek research watershed. And we did this in March of 2022, and we incorporated RTK surveyed ground control points on the snow surface to produce a highly accurate digital surface model of the snow surface elevation. To calculate snow depth from this, we simply need to subtract a snow-free elevation, which we produced using a similar EB drone in September of this past year. And so the result of this was a high resolution 10 centimeter snow depth map created for the entire 7 square kilometer study area. And for this project, we clipped it down to a much smaller ice-wedge polygon field that we also instrumented with other sensors later in the season. And we've been doing this, as I mentioned, since 2015 at this study site, and so we have lots of validation data to be confident that the methodology works, and we've actually published on this as well. But we needed to build on this a little bit for this project here. And as a hydrologist interested in surface water, we need to know more of just where the snow is located. We actually need to be able to quantify the amount of water stored across the landscape. And we do this by estimating snow water equivalent, or SWE. So our goal here was to incorporate field observations to spatially distribute snowpack bulk density across the landscape. There's many different ways to do this. You could use complex models. You could use a simple average snow density, but the problem with those, they're not exactly suited to these tundra snowpacks. And if we just apply a simple average snow density, it doesn't adequately represent the large spatial variability we find in snow density across the landscape. So to do this, we explored an empirical relationship between observed snow depths and the corresponding bulk snow density that we collected using snow cores. So a logarithmic equation provided the best fit for this data, and it was incorporated into our model to estimate spatial variability and density based on our snow depth. And the figure here shows these in situ measurements, which we also RTK surveyed and used a subsample for ground validation. But we can note that there's a pretty large variation in the strength of the relationship as you move across different land cover types here. So using the snow depth maps, density map was produced at the same resolution, and to calculate SWE, you just simply need to multiply the snow depth by the corresponding density for each pixel across your study area. Here we see our SWE map for a polygon site at 10 centimeter resolutions. By comparing the SWE here to the surrounding area, we found that our polygon site in general acts as a net sink of snow, which is resulting from blowing snow accumulation in the low-lying terrain over the course of the winter months. And when we look at the averages and compare it to the larger basin averages, we find that there's about 14% more SWE or more water being stored in this polygon site here. So we can also see that SWE varies greatly by the hill slope scale, which is something that's often overlooked by traditional snow survey methods that focus on a point, or larger coarse remote sensing methods that focus on regional differences here. So understanding the distribution at the fine scale is quite important. And if we zoom in a little bit here, we can use these maps to clearly outline the patterns and highlight the spatial distribution of the snow. Here we find that the polygonal trough areas, so those low-lying areas between the larger plateaus, act as a net sink of snow where blowing snow is deposited and builds up in these areas. And we can actually start to quantify the changes here. So we found that just at this site alone, there's about 15% more water being stored in these troughs than the surrounding plateaus of the ice-wedge polygon field. However, I should mention that this is probably an underestimation here because there's also vegetation within a lot of these troughs, and that's something that's very hard to filter out in the digital surface model. So we might actually see larger quantities of stored water in these troughs. Now we tried to mitigate this by editing the point clouds from the drone data, but you can't simply remove all vegetation. So we might have a little bit of an underestimation there. And so we also observed deeper snow depths and thus more SWE on steeper slopes that are downwind of the dominant wind directions, which result from blowing snow events. And there's a great example of this in the polygon site here, where you see this large drift where we found our maximum snow depth of almost 2 meters and a very large SWE value. And this is actually a result of snow being trapped by vegetation on the landscape, resulting in this large drift in the downwind area. And so this is caused by things like tall shrubs and small clusters of spruce trees that effectively act as a snow fence and trap snow. And so these drifts are also important because the snow that's found in these areas lasts much later into the melt period. And so why is that important? Well, the snow that remains in these deeper snowpacks, such as the troughs and these drifts, as you can see in this image here, they effectively insulate the ground from incoming solar radiation during the spring snowmelt period. And so they can actually have been found to delay the thawing of the active layer in these areas, which is important if you're trying to understand the degradation and melting of ground ice features such as ice-wedge polygons. You need to be able to understand what the snow conditions are like at that site. So as I mentioned, snow is one of the main controls on the ground temperature, and this is effectively because snow is such a great insulator. As we increase temperatures across the Arctic, we have observed ice wedge polygon decay, and the increased amount of snow that might be trapped in these areas, can effectively speed that process along. And so this is just a first step. We instrumented an ice wedge polygon field this summer to look at the ground thermal conditions. So collecting data is the first step for developing advanced hydrological models and understanding future changes to thermal karst lakes. And so we need to understand how the snow and the ground temperature might be influencing draining thermal karst lakes in the area. And so with that, I want to say thank you and acknowledge the many people who have been involved in this project. And if you have any questions, feel free to send me a message. Thanks.